Right, it's time to Laplace it up. And we're going to do that with this heat equation, which has some boundary conditions. So let's recall some general rules. So that's the Laplace symbol, in case I start getting a bit rubbish with drawing it. Just remember that is the Laplace symbol. So obviously if you Laplace this txt, you're going to get t, and we're going to do a little squiggle once it's been Laplaced up. And that's going to be the same as if we write it in the exponent. So it's going to be e to the minus st txt dt. So the Laplace properties of this is going to be the Laplace of dt. And also, just for clarification, you'll generally see this written as a delta, but a delta is kind of like a squiggle, like a flick back. I'm not going to do that here because it's just painful and it looks silly and I can't draw it, but that's what it actually is meant to be. So that's going to be an st with a little squiggly, x minus s minus t, x minus naught. So these are Laplace transforms. I think in most tests and exams you're given a Laplace table, but if you aren't given one, then you just need to remember these. So let's sub this cheeky boy into the equation. So this is going to equal this, isn't it? Because if this Laplace of that is equal to the right hand side, so let's sub in the initial condition of tx0 equals sine cubed pi x into this, which is the left hand side. So you're going to get d2t dx squared minus st is going to equal, because obviously we've deducted this from one side, and it's going to be minus, because remember that's minus, and that's going to be sine oh, that shouldn't be cubed. That should be a 3 actually, shouldn't it? Yeah, 3 pi x. Let's do that. 3 pi x. So I don't know why I think I wrote that silly. I should write that again. 3 pi x. So now it's going to be minus sine 3 pi x. So this is a non-homogeneous linear ODE. So we need to now solve the homogeneous part, where h, that's the homogeneous part, dx squared minus st, h, the homogeneous part, equals 0. We know that there's a general solution of t h x would equal ae, and we would have the root of sx plus b e to the minus root sx. So that's our general solution. The particular solution is going to be tp with a little squiggly over the top. That should have a little squiggly over the top as well. tpx, which would be c sine 3 pi x. And it's the same form as the right hand side. So now we can take these, similar to when we're doing videos on solving second order differential equations. I've got tons of those on this channel, as well as an entire playlist dedicated to it. We now sub these into our formula. So you're going to now get d squared over dx squared, and we're going to get c sine 3 pi x minus, let's do s, c sine 3 pi x, which is going to equal minus sine 3 pi x. That's a double differentiation, and we're going to crack into that. So we can now start cleaning up. So c minus 3 pi squared. Oh no, sorry, the squared should be on the outside of the brackets. That was cheeky. Sine 3 pi x minus s c sine 3 pi x, which is going to be equal to the right hand side, which is minus sine 3 pi x. We can now clean up even further. So you're going to get minus 9 pi squared plus s sine 3 pi x, which equals minus sine 3 pi x. But guess what? We can obviously divide both sides by sine 3 pi x, and that's going to disappear. So therefore, c is going to be 1 over 9 pi squared plus s. There's a minus there, bada bing, bada boom. So we now can go back to xs and recall over here. Again, probably the stupidest and messiest thing I've ever done. And we know that ae to the minus sx plus b to the e minus root sx plus sine 3 pi x divided by s plus 9 pi squared. We can now apply the boundary conditions, because obviously what we do is we've added them all together, but remember we're now going to apply the boundary conditions. This is very similar to when you solve a second order linear, non-homogeneous or even homogeneous differential equation. So that's how you get this. But now we're going to apply that. So x equals 0. So that's going to be a plus b plus sine 0. Because obviously we put 0 in here, 0 in here, 0 here. Sine 0, s plus 9 pi squared. You're going to get a plus b equals 0 or b equals minus a. When x equals 1, you will now get a e to the root s plus b e to the minus root s plus sine 3 pi s plus 9 pi squared, which is going to equal, I'm going to go over here, a e to the root s minus e minus root s. Why has this a come out? Because these ABs, remember, b equals minus a. So we can substitute this b for a minus a and then just pull the a out. That's a genius. That is a techie move. That is a seriously good move. But we also know that sine 3 pi equals 0. So ae root s minus, sloppy with the brackets, you know. E to the minus root s would equal 0. So a would equal 0. So a equals b, which equals 0. So they all equal 0. So the simplified solution is going to be t xs equals sine 3 pi x divided by s plus 9 pi squared. But we now have to remember the inverse Laplace of 1 over s plus a. Again, this is in your table, or you should remember it if you've done enough of these. So if we do the inverse Laplace, the Laplacian, well, who knows what's going on. I don't know how long this video's been, like 3 hours. Txt would equal sine 3 pi x e to the minus 9 pi squared t. Because obviously we've inversed it. So we've inversed this baby. Doing that, we've got that. And we have Laplace transformed a heat equation with these naughty little boundary conditions. What more could you ask for?